Okay, so I want to talk about differential operators and do a little bit of an introduction. An operator is, you can think about it as a function that takes functions as its input and has functions as its output. So an operator is a function on functions. Let me give you an example of what I mean by that, because that's a mouthful to say and digest. So, for example, maybe we'll have the operator D for differentiation. So you take in a function, you do this thing to it, and that's going to output a different function. Differentiation. Okay, so for example, I might have d of one function is going to be another function, and maybe my original function that's my input is the function y equals x squared, for example. And the output is going to be the function y equals 2x. Now I'm writing this in different colors. This isn't really a very correct equation. I'm using this color y equals x squared to indicate the function that takes x to x squared, and I'm using this to indicate the function that takes x to 2x. I'm not saying that d of something is equal to y is equal to 2x. That's why I'm using these different colors to try to make that clear. But don't actually write this at home. But that's just to sort of give you an idea of what the idea that you're inputting a function into this differential operator and outputting a different function. Okay, now I want to think about functions as vectors. So we've talked in this class about how vector spaces can be generalized to where you're not just talking about sort of the vectors that we started out with in linear algebra, but you can talk about more general vectors. So for example, the function y equals x squared, I can think of this as a vector. I don't know why this eyedropper thing is here. Let me see if I can. Oh, it's gone. Great. Okay, you can think of that sort of as a function, or as a vector, but an infinite vector. An infinite dimensional vector. Let me just give a few of the coordinates, and to sort of give you an idea of what's going on here. So maybe y equals x squared at -5. I'm just going to put, I'll get a different color actually. A vector, it's going to be a certain value at -5. It's going to be a different value at -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5, and so on. And so maybe its value at -5, well, if it's y equals x squared, we know its value at -5 is going to be 25. And at -4, it's going to be 16. We're going to have 9, 4, 1, 0, and then 1, 4, 9, 16, and 25. And if you imagine a vector like this that's infinite in both directions, and not only has the integers, but has stuff in between, if you can sort of just imagine that there's infinitely many more entries in between even all the ones that I've written down, then that sort of gives you an idea of how you can sort of think about a function as a vector. It's got one coordinate that tells you what value it takes at -5. It's got another coordinate at -4, but there's infinitely many coordinates, and even the ones in between, there's infinitely many even in between that I haven't even written down. So let's say I take that vector and I turn that into a vector that looks more like at -5 it's going to be 10, at -4 it's going to, or maybe -10, it's going to be -8, it's going to be -6, -4, -2, 0, 2, 4, 6, 8, 10. That would be that would be y equals 2x. So this vector is the function y equals x squared. And don't actually write vectors this way. Obviously, I'm just I'm not writing the whole vector down. First of all, this is not a correct way to express this vector in any sense. I'm just trying to give an idea of how it sort of makes sense to think about a function as a vector. So this function would be y equals 2x. And so you can think of differentiation as a linear transformation from a vector space to another vector space. All right, so if V is the space of all infinitely differentiable functions. And by infinitely differentiable, I just mean you can differentiate it, and then you can differentiate its derivative, and you can differentiate that, and you can just keep going as many times as you want to. Infinitely differentiable functions. It's a little secret. Sometimes we don't write out the whole word differentiable, especially when our software to record the screen messes with our Wacom tablet. Okay, so for example, we've said our first example was differentiation, which we're going to call D. D is differentiation. Put a little period there to differentiation. Okay, so d of x squared, and we can write it this way, maybe. D of x squared is 2x. So when I say x squared here, I really mean the function y equals x squared. Okay, I don't mean, so if I said d of x equals 1, whoa, d of x equals 1, I'm not talking about a function d that's just defined to be 1 everywhere. No, I'm taking as input the function y equals x, and I'm outputting the function 1. So my input isn't a number, my input is actually the function y equals x. And that's maybe why I have a little bracket here instead of parentheses, just to make it clear that I'm not talking about taking a number as an input and outputting another number. Okay, so d of sine of x, if I input the function y equals sine of x, I'm going to output the function y equals cosine of x, and so on. You can see how this is going. Whoops. Let's do one more with this d differentiation operator. We'll say d of, what is, if we have x raised to some k times e to the rx. What's that going to be? And it's going to be the, let's see, we're going to use the product rule here. So it's going to be kx to the k minus 1, and there's a reason I'm doing this one specifically, times e to the rx, plus x to the k times r e to the rx. So I'm going to put my r out here, and I got e to the rx. Okay, that's enough of that differential operator. Now I want to talk about a couple more. So what does d squared mean? Well, d squared means I'm going to differentiate twice. So d squared of x squared means the second derivative with respect to x of x squared. Trying to write too fast and my tablet's not keeping up with it, and that would just be 2. Okay, d squared of sine of x is negative sine of x. All right, how about this one? What if I have the operator d cubed plus d? So that's another operator. And let's say I take that operator and I apply it to x to the 5th. So what would that mean? It means I take the 5th derivative, or the 3rd derivative of something, and then I add the 1st derivative of that thing. So d cubed plus d applied to x to the 5th is going to give me, let's see, the 3rd derivative is going to be 5x to the 4th, 20x cubed, and then 60 x squared. That's the 3rd derivative, plus the 1st derivative, so plus 5x to the 4th. All right. Let me do a couple. Oh, here's another one. What is 7? Let's say I just have 7 is my operator times x to the 5th. That's just going to be 7x to the 5th. So it just means if my operator just kind of looks like a constant here, that just means I multiply it by a constant. So kind of exactly what you'd think. Okay, so what is d plus 7 applied to x to the 5th? Well, that just means I take the derivative, which is 5x to the fourth, and then I add 7 of the original function. So 5x to the fourth plus 7x to the fifth. Okay, so just like d cubed plus d means I take the third derivative and then the first derivative, d plus 7 means I take the first derivative and then 7 times the original thing. Okay, maybe I could ask what is 3d minus 4 applied to x to the fifth. And maybe for some of these you should pause it and see if you can figure out what it is before I go ahead and roll on. So the derivative is going to be 5x to the fourth, and then I multiply that by 3, so I'm going to get 15x to the fourth minus 4x to the fifth. All right, we'll do another one. How about d minus 2? Oh, I need to plug in my computer. Let me pause this thing. Okay, I'm all plugged in now, and I want to do d minus 2 applied to the function, let's take x to the fifth plus e to the 3x. Okay, so what do we think that's going to be? Again, you can pause here and do it, and maybe that would be a helpful exercise. Okay, but we're going to take the derivative first, so that's going to be 5x to the fourth plus 3e to the 3x minus, then we're going to have 10x to the fifth minus, minus 2 times x to the fifth minus 2e to the 3x. We're not taking 2 times the derivative, just 2 times the original function here. Okay, and so that would end up giving us our 3e to the 3x and our 2e to the 3x. We could combine those terms if we wanted to. I won't maybe do that right now. And now what is d... Oh, let's see. Let's take d minus 2 now, again, times, and this time I will take it, and I'll apply it to the function x to the k times e to the 2x. Okay, well, what's that going to be? Well, we already looked at what is d of x to the k times e to the rx, so that's up here. We can do that again real quick. It's just a quick application of the product rule. So k x to the k minus 1 times e to the 2x plus 2x to the k e to the 2x, right? It's the derivative of e to the 2x times x to the k. So 2x to the k e to the 2x but then we need to subtract 2 of the original thing, minus 2 times x to the k e to the 2x. And what do I see? I see that 2 of these terms are going to cancel, and I just end up getting k x to the k minus 1 times e to the 2x. Okay, so that's interesting. This is going to turn out to be important later. Okay, for now we'll leave that at that as just some practice with these operators. Okay, maybe one more thing I want to do. Yeah, at least one more thing that I want to do is say, what would d plus 3 squared, what would d plus 3 squared applied to, let's say, x to the fifth? What would that mean? Well, there are 2 possibilities maybe for what it could mean. So let's think about what it might mean. So it could mean d plus 3. Remember, this is an operator, so d isn't a variable or anything like that. It's not like I'm multiplying a variable by x to the fifth. I'm applying some operator to x to the fifth. So maybe if I rewrite it this way, you might think maybe that first I do the operator d plus 3 to x plus fifth, or x to the fifth, and whatever function I get out of that, then I apply d plus 3 to it again. So it would be like a composition of operators. Composition of functions, right? Because an operator is a kind of function. It's just a kind of wacky function that takes functions as inputs and outputs more functions. Or does it mean, let's assume that I just kind of blindly expand this thing, foil it out, and hope it works, right? Maybe it means d squared plus 6d plus 9. So that would be a different operator, and maybe I could apply that to the function x to the fifth. So which of these two things is it, or are they the same? I'll put a question mark here. Okay, are they the same? Well, let's check. Let's first do this composition one. So let's try to do d plus 3 applied to x to the fifth. D plus 3 applied to x to the fifth is going to be 5x to the fourth plus 15, plus 3 x to the fifth. It's not a very good 5. Whoops. Let's try that again. 5x to the fourth plus 3 x to the fifth. That's a worse 5, but I mainly wanted it to be an exponent position. There we go. Okay, d plus 3 times applied to x to the fifth is going to be this new function here, and then I want to apply d plus 3 to that. So d plus 3. We'll go do that. D plus 3 applied to 5x to the fourth plus 3x to the fifth. What is that going to be? Well, let's see. That's going to give us 20x cubed, right? Because I just differentiate the first thing. 20x cubed plus, and then 15x to the fourth. And then I'm going to take 3 times this whole thing, and that's going to give me another 15x to the fourth plus 9x to the fifth. Plus 9x to the fifth, and there I am. Okay, so that's if I apply this d plus 3 operator twice. On the other hand, if I were to just go ahead and full steam ahead, say d squared plus 6d plus 9, my computer and tablet have had enough of each other. Okay, here we go. D squared plus 6d plus 9 applied to x to the fifth. What is that? Well, if I take the d squared part, that would be the second derivative of x to the fifth. So 20x cubed plus, let's see, plus 6 times, what's the first derivative? 6d, it's supposed to be a d anyway. The first derivative would be 5x to the fourth. And then plus 9 times x to the fifth. Remember that 9 is not a constant, it's 9 times the original function. plus 9x to the 5th. Okay, so are these two things the same? 6 times 5 is 30, so I've got 20x cubed plus 30x to the 4th plus 9x to the 5th. Yes, they are the same. So they are the same. Okay, they are the same. Now, why would they be the same? That's the last, well, since this video is already over 20 minutes long, maybe I'll just let you sort of think a little bit about why these might be the same. But the shorthand way to think about it would just be to look at first this d plus 3 applied to d plus 3 applied to x to the 5th, and sort of just think about what that means. So it means we're taking the derivative of this whole thing, and then we're going to multiply 3 times this whole thing, and just sort of expand all of that out, and use the fact that you can pull a constant out of a derivative. At one point you're going to have to use that as well, and you'll see why these two things end up being the same. And maybe more generally, looking at that will help you see that when you factor, that you can sort of factor differential operators just like you can factor polynomials. And so there's sort of a correspondence in a way between differential operators and polynomials, and that's one of the really important things that we're going to exploit. It's really the important fact that we're going to exploit with the annihilator method, and I'm going to start that in the next video.